This is an RNZ podcast.
Kia ora, and welcome to Elemental. I'm Allan Backman from the Auckland University of Technology.
And I'm Alison Ballance. In this podcast from RNZ, we are celebrating the International Year of the Periodic Table by visiting all the chemical elements, from the most well-known to the most obscure, the latter of which applies to today's element, I think.
Oh yes indeed, it's holmium, folks. Probably not a very well-known element to those of you outside the chemistry field. If it had a catch cry, it would probably be something like really obscure but a really important surgical laser.
Well, its name, Holmium, makes it sound wholesome somehow, but of course Holmium doesn't have the W on it, it's spelled H-O-L-M. But actually, I can't begin to guess where that name comes from.
So holmium comes from the Latin Holmia, which was in fact the name for Stockholm in Latin.
So we had another Latinised city name, and that was Hafnium, wasn't it, for Copenhagen?
Yep, indeed. But actually, it has much more in common with erbium and the Swedish village of Ytterby. Holmium is another one of these lanthanoids, vital statistics, elemental symbol HO, atomic number 67, and discovered in 1878. And as we have gone through many lanthanoids in our journey so far, you'll not be surprised to know that its discovery was typically tortuous and started with a sample of yttrium, and then that was found to be impure, and that was found to contain both erbium and terbium. And then the former, the erbium, was found to contain both ytterbium and holmium, hence the link to that little village outside Stockholm called Ytterby.
These lanthanoids are very tricky. Is holmium common?
It's about the 56th most abundant element in the Earth's crust, which, puts it sort of around about halfway-ish. And in terms of abundance, holmium obeys a thing called the Oddo-Harkins rule.
Tell me more.
Oh, yes. So it has an odd atomic number, and what we find is pretty much a rule for all of the elements is that the abundances of even-numbered elements are greater than the abundances of odd numbers. And so what we find is the abundances go up, down, up, down, up, down, up, down, all the way through the list of elements on the periodic table, which is kind of interesting. So holmium itself is less abundant than its immediate even-numbered neighbours, which are, if you can remember, dysprosium and erbium.
Yes, we have done both of those.
We have indeed. But in fact, of the odd-numbered lanthanoids, it is in fact the most abundant. And the whole odd-even thing, the Oddo-Harkins rule, is all to do with paired protons being more stable than single protons. But then we're getting into nuclear physics and we're not going to go there.
That's right, because you're a chemist. Anyway, does holmium have any notable features?
Oh, every element has notable features, Alison, goodness. So, like many of the lanthanoids, its most notable feature is its magnetic properties. And the particular claim to fame for holmium is that it has the distinction of having the largest magnetic moment of all the elements, which is kind of interesting. And so therefore, if you want to make a magnet stronger, what you do is put a piece of holmium at both poles and you'll end up with a stronger magnet because of holmium's magnetic properties. The trouble with this is that it doesn't retain the magnetic field in the absence of the magnet, though. And our last episode, we were talking about helium, and it's important in cooling MRI superconducting magnets. Holmium is, in fact, one of the elements used in said superconducting magnets.
Now, while we're in hospitals, and you mentioned surgical lasers at the beginning, so now would be a good time for you to tell me about holmium and surgical lasers.
Okay, these have the wonderful name HOYAG lasers. So that is short for holmium-doped yttrium aluminium garnet, of all things. Now, how do these work? Well, they give out light that is invisible to our naked eye, but it's out there in the infrared, so radiation around about a wavelength of 2,100 nanometers. And this wavelength means that the radiation is going to be very, very strongly absorbed by water. Now, as you know, there's a lot of water in the body, so this combination of factors makes these lasers really, really ideal for making precise cuts in tissue during surgical procedures. Because of all the water, you know that that's going to absorb basically all of the energy of the laser within a distance of around about 0.5 millimetre or so. So you're talking very, very, very precise cuts to very, very precise depths. Even more useful is that these cuts also self-cauterize, so you don't need stitches and stuff like that. Because of its broad range of surgical applications, these Holmium YAG lasers, by the early 1990s they were being called the Swiss Army knife of lasers.
That's lovely.
They're also very, very useful if you've got urinary stones. You can use these lasers, shine them on the urinary stones, and then they break up into smaller particles and that hopefully can be painlessly excreted.
So surprisingly useful in hospitals. Interesting fact, please.
Okay, so in 2017, and this was quite remarkable, a single Holmium atom was used as a computer bit by IBM. So we know that computers work basically in binary, so they're reading zeros and ones. So this single Holmium atom was basically able to be read as either a 0 or a 1, owing to its magnetic properties. So this is quite extraordinary for certainly the future of data storage. If we can get single atoms being interrogated to give an answer of either a 0 or a 1, then this is going to massively, massively increase the way that we can store data. It's an order of magnitude at least over what we've got now.
Well, in terms of computing, we'll keep our ear out for Holmium, and maybe one day we'll hear a bit more about this obscure element. But in the meantime, you can find out more about some of Holmium's lanthanoid relatives in previous and in future coming up episodes of Elemental at rnz.co.nz/chemistry.
We're also a podcast, and you can find us at your favourite podcast provider. Next time, we finally make it to number 1 on the periodic table, hydrogen. But until then, it's goodbye from me, Allan Backman.
And me, Alison Ballance. Mā te wā.